102. Greg Moore always has like 400 slides, and at the bottom it has, you know, slide X of 405.
Okay, so welcome back. We'll start the afternoon session, and we've got Dan Thompson from Swansea telling us about aspects of E-models or epsilon models. E-models.
Okay, thank you very much, Manuel. Thank you to the organisers. It's a pleasure to be here at this very nice workshop. Apologies, I missed some of your talks yesterday. I hope to catch up on that. But here we go. I'm not sure how much of this title I'm actually going to talk about. I left it quite vague to give me a bit of scope. But since Lucas found these brilliant results on Thursday and Friday, that part of the talk has grown and the other part has shrunk, and we'll see what happens. Okay, so I'm going to talk mainly about work that I've been doing recently with Lucas Scheppers, who is my finishing grad student, and he's here today. And I'll also potentially speak some hints of some work with Alex, who's here, Lewis and Andra, who I don't believe are. But mostly, I think I'll talk about this, but we'll see. So this is a talk in two parts, and they're kind of a bit distinct, so we'll see what happens. So I'm going to talk about resurgent aspects of lambda models. So lambda models are a type of integrable deformation, and that's sort of the topic of this conference, so hopefully many of you know what I'm talking about here. Resurgence is something that's less familiar in general, so I'm going to try and outline a little bit about that, and then apply some ideas of resurgence in the framework of integrability. And I should caveat myself, I'm not presenting you some new conceptual breakthrough here. This is a case study of some techniques that have been developed over a number of years, and there have been a number of recent breakthroughs in the last 12 months, actually, and I'm going to put them all into action on this particular model, and hopefully we can learn something. Okay. So, as we all know, perturbation theory is brilliant. Right? You want to calculate the anomalous magnetic moment. So you calculate a vertex, you do a one-loop vertex correction, and you do this for 7 loops in QED, and you get this result. This is, I think, a 7-loop calculation, I think. Amazing. And then you ask the experimentalists to do the experiment, and you find just this incredible precision. So perturbation theory is our bread and butter, and it's amazing. But this should cause sort of cognitive dissonance, because at the same time as it being amazing, it's also fundamentally terrible. So in general, perturbation theory is an expansion in some coupling, G, whose coefficients grow. And they can grow for 2 reasons. They can grow just because you have a lot of Feynman diagrams. That's one source of growth. Another source of growth is actually when you do the integrals themselves, that can produce some extra factorial behavior. And, you know, you try and sum a factorially divergent series, and, well, that's not finite. So what do? This is a disaster. And typically what we do is we do as many loops as we can calculate, which is probably 7 if you're really strong, and then we stop and walk away. Actually, that's a good idea, because if you kept going, after a certain point, your calculation would get worse, and worse, and worse, and worse. So that's called truncation. But still, we could ask the question can we make some formal sense of perturbation theory? And does this actually mean anything? Is there some physics here? So is this terrible disaster physical? And of course the answer is I'm going to claim yes. And I'm going to claim this is something that you actually know. And this is the idea of resurgence, which is how non-perturbative contributions correct and understand this factorially divergent behavior of perturbation theory. And in this context of quantum mechanics, this is really well established. And really, the question is, quantum field theory? Can we make this idea fly at quantum field theory? And that would be giving us a mathematically precise meaning for what quantum field theory is. Okay, so here's a potential, V. It's a double well, which means it looks classically like there's a degenerate ground state. Yeah? The potential's the same in both holes. And then you calculate the wave functions, and there's an even one and an odd one. And helpfully, Mathematica didn't put the label on the left-hand side of the plot to tell you which one's the ground state and which is the first excited state. But that's an exercise in Sturm-Liouville theory, so I'll leave you to convince yourself the answer to that. But what happens is, it's not that there's a degenerate ground state. There's a splitting of energy levels. And the splitting is mediated by tunneling, instant-on effects. So, suppose we don't know about the instant-on effect, and we just work in one vacuum, and we do perturbation theory. Indeed, here we will find some factorially divergent series. That's what happens. So you do Rayleigh-Schrödinger perturbation theory in that vacuum, work out your energy level, and you find a factorial growth. But the instant-on contribution kicks in, and this is a typical instant-on fugacity, e to the minus 1 over g squared. The coefficient here is quite important, this coefficient A. So this A here and this A here are the same, and it's twice the instant-on action. And it's twice because the tunneling goes from one to the other and back round. Okay? So instant-on tunneling lifts the degeneracy. Nonetheless, let's just try and understand a bit better how to examine this series. So I'm going to now teach you for 2 slides the core techniques of all resurgent analysis. So ask questions on these 2 slides because that's a useful thing to learn. Okay, so we're going to use a technique called Borel summation. Now, I'm going to jazz things up a little bit in this talk. I'm going to consider series that have 2 parts. So in blue, I'm going to have an alternating part. Right, so there's a minus 1 to the n here, plus, minus, plus, minus, plus, minus, and a non-alternating part. And I'm going to try and keep this convention. Red is non-alternating, blue is alternating. And there was a clever reason for red and blue to do with magnets, but I don't understand it now. But these coefficients, an, plus and minus, are factorially growing. So what we're going to do is we're going to take this asymptotic series, it's not well defined as is, but we're going to define a new series, which is well defined, by taking each term of it and dividing through by m factorial. So we're just going to smash out this factorial growth. And we've got a series here that we can sum, has a non-zero radius of convergence. That's great, so we've completed this sum. But now we want to go back to our original series, and the trick is to use this expression for m factorial. So we can write m factorial as an integral, actually as a Laplace transformation. So if we Laplace transform back, we get an answer for this summation. So roughly speaking, what are we doing? We've divided by m factorial, but we're putting m factorial back in as an integral, and we're swapping the order of summation and integration. That's the black magic there. And this is fantastic. This works. This can give you a finite answer. But, and there's a big but here, and this is where all the interesting stuff happens, this integral here needs to be well defined. In particular, what do you do if the integrand has some cut or pole along the integration contour? And this example illustrates that. So I've done my Borel resum of the series. I've got a blue bit here. This has a pole at t is minus 2. Well, that's fine, because that's not in 0 to infinity. But the red bit has a pole at t equals 2. And that is, t equals 2 is on this contour. So this integral isn't well defined. So we have to do something. And the thing we're going to do is we're going to change the direction in which we integrate. So rather than integrating along the positive real line, we're going to integrate at an angle above the real line. So we're going to skirt around, go above all of these poles and potentially cuts and all sorts of stuff that can happen along this real axis. And since the function is nice, integrand is nice along this contour, we can do the integral. So that's great. But of course, you know, nothing's telling us to do that. We could have equally have gone below. And that would give us a prescription for the integral. So we've got an integrand that can depend potentially on the direction in which we're integrating. And indeed, as you pull this integration contour through the cut, you can get a jump. You can get a jumping phenomena. So this prescription gives us a finite but ambiguous answer. So we've gone from no answer at all to a finite but ambiguous answer. So the difference between integrating above the contour, above the cut and below is 2 pi I e to the minus a over g, something like this. So two factors here. First, pure imaginary. That's interesting. So the real part is non-ambiguous, but the imaginary part is. And there's a weight here, and it's the same instanton fugacity that we had before. And this is how the perturbative series is talking to the non-perturbative series. In fact, what's going to happen is the non-perturbative sector is also ambiguous. And it's ambiguous in a different way. It's not like you have to do a large order analysis. It's actually ambiguous at leading order, because you're looking at instanton, anti-instanton pairs. There's a moduli space that you need to integrate over, and that integration over the moduli space, some quasi-zero mode actually, there's a potential, is ambiguous, and you need a prescription to treat that integration. And what was shown by Bogomolny and separately Zinjastan was that this ambiguity here is exactly the same and opposite the ambiguity in the non-perturbative sector. So that's kind of amazing. You take this perturbative series that's badly defined, factorially growing, you add to it your non-perturbative piece that's also badly defined, but miraculously added together, the whole thing is well defined. And that's the idea of a trans series. Okay, and this has a very long history and a lot of recent work, and there is much more, and I apologize to names I've missed. Okay, so that's the sort of techniques behind resurgence. Any questions at that point?
Is there some theoretical explanation why it should be the case?
Well, there's a physical thing, which is physics should be well defined, and you know, my energy should be real. Okay, the mathematics, that's really, you know, murky mathematics now. This is Ekal's theory of trans series, which is not fully developed or understood. That you can add up all these potentially infinitely many divergent series to find a well-defined answer. Yeah.
I was just wondering, does it somehow miraculously always give you all the non-perturbative physics, or just the non-perturbative physics that you need to make the perturbative stuff?
Good. So this is a nice point. Okay, so so the punchy resurgence conjecture is that the perturbative sector knows everything. Everything. That's quite punchy, and I'm not sure to the extent to which that's, you know, fully accepted. Here, for instance, the perturbative sector doesn't know about the one instanton event. It knows about the instanton anti-instanton event, okay? But it actually knows a bit more than that, because if you then do fluctuations on the instanton one anti-instanton event, that itself is an asymptotic series that resums, that knows about the 4 instanton event, which resums to know about the 6 instanton and so on, and that's all implicit in the perturbative sector. So the perturbative sector knows a lot. Okay, and that's this idea of a resurgence triangle. Okay, so look, I think this idea is beautiful. But there are many open questions. I think if you could expose the resurgent structure of, 4D Yang-Mills, you'd be a rich person. But before you can do that, there's quite a few things, which is, what about theories without instantons? What about when we're not really talking about quantum mechanics, but actual quantum field theory? What's happening with renormalization? How does that talk to these resurgent observables? Lots of other subtle questions about the role of complex saddles. In fact, this is particularly important in the context of gravitational path integrals and stuff like that. So there's lots of stuff going on here. And the philosophy here is that I can't do four-dimensional gauge theory, but maybe one plus one dimensional integrable models are a good place to start because they're calculable and they can share some interesting RG profiles. They can be asymptotically free, they can be confining. In fact, the theory I'm going to talk about is gapped in the infrared and completed in the UV with a CFT, which I think is kind of cool and maybe says something about physics. Okay, so I'm going to talk a little bit first about some older work. This was work initiated with Saskia a long time ago, but then also pursued with Lucas last year or the year before. And I reported this on the online version of this series. I know not everyone was there, but so I won't dwell on it too long. Where I've been considering Yang-Baxter and bi-Yang-Baxter type deformations of the principal chiral model. Does everyone know what a Yang-Baxter deformation is? Does anyone not? You're in the right room. Okay. So the strategy we're going to do here is we're going to try and find the equivalent of the instantons that can be related to these Borel poles. That's what our aim is. So to try and identify the classical saddles, or semi-classical saddles, that source the breakdown of perturbation theory. And we do this in a bit of an indirect way, basically as advocated by Alexei Mitat and probably some other people, Gerald. We're going to, instead of considering the quantum field theory in R2, we're going to reduce it on a cylinder with some twisted boundary conditions. It's like turning on a chemical potential. And the claim, and this is where I think there is a bit of hand waving, is that when we do this reduction, we're adiabatically connected to the theory on R2. We're not going through a phase transition, and we're kind of accessing enough information about the theory on R2 to be reasonable. And there's some evidence for that claim, but we'll take it. So we're going to reduce from the two-dimensional deformed principal chiral model to quantum mechanics. We're going to look at the large order behavior of that quantum mechanics, just like we did with the double well. We're going to find the Borel poles. There's a little trick here, a Borel pade. I don't know if I've got time to tell you about that. And when we found the Borel poles, we're going to pay close attention to their location, because the location of the Borel poles, that was the instanton action. And we're going to find instantons in the quantum mechanics that source these Borel poles. But even more, we're going to find genuine two-dimensional quantum field theory configurations, finite action saddles, which then fractionate into instanton, anti-instanton events when put on the cylinder. Okay, so please stop me. This next slide, the next slide is a 40-page paper on one slide, so I'm suppressing quite a lot of detail.
So why you should expect non-barrel non-summability? Why it can't be barrel summable?
Well, you can get Borel summable contributions, but typically just you can get an alternating piece, a non-alternating piece. You get what you get. You have to do the calculation to find out what you have. Okay, so here we go. This is this 5-step program I just outlined. So I'm going to consider here what's called the bi-Yang-Baxter model, This is a two-parameter squashing of the sigma model whose target is a 3-sphere. So SU2 theory. I'm going to do twisted boundary conditions. So as I go around the circle, labeled by X, spatial circle, I'm going to twist by e to the I sigma 3. And I'm going to keep only the lightest modes. So I'm going to parameterize this matrix in some way and throw away heavy modes in the reduced theory to get a quantum mechanics with a particular potential. And it turns out the potential you get for this double deformed model is some elliptic potential. Okay, so there are two deformation parameters, one here and one here. And these are elliptic functions, so there's an elliptic modulus that also depends on the deformation parameters. So this is some particular quantum mechanics that's actually studied for fun anyway. Interesting side remark is it's related in some way to n equals 2 four-dimensional gauge theory with 4 flavors, nf equals 4. I don't know why, but there we are. Okay, so we've got this quantum mechanics, and then we can just do perturbation theory, WKB perturbation theory, or some variant of that, to work out the ground state energy. And because this is just put on a computer, it's a recurrence relation. You can crank it for as much as you want, and you get up to 100 orders of perturbation theory, no problem. Here's the first couple of terms. This is maybe for eta is a half and zeta is a quarter, or some random selection like that. But you can keep going. And these numbers start growing massively. So you need to set precision, numerical precision, 100-digit precision in your Mathematica.
You have coupling G.
Coupling G,
and the field G.
yes, that's not very good. G is H bar, right? So yeah, that's unhelpful. It's alpha prime, I suppose. But yeah, this G was the 2x2 matrix, and this G was the coupling. Apologies. Okay, so we get this series, and then we find the Borel poles. So we do our Borel transform, and we plot the Borel poles. And what's not so clear here, but I'll have to explain in words, is there is a cut here that is starting at the location of this red circle, and there's a cut here starting at the location of this blue circle. The one nearest the origin is normally the dominant thing. So there's an alternating and a non-alternating piece. Okay, this is just a quantum mechanics. So you can find instantons. And here's the instanton action. And it turns out this position of this pole varies as we vary the parameters of the theory. And the instanton action also depends on the parameters of the theory, and they precisely match. So that's great. So this really does match this location. The cut on the left is a bit harder to explain. That doesn't come from instantons. It comes from what are called complex instantons. So you need to consider complexified field space to identify these solutions. But they exist, so there are some complex field configurations, ones that you'd normally just ignore, but you shouldn't. And they source this cut. So that's just at the level of one dimension. But the cool thing is that this actually arises from a finite action solution in 2 dimensions called a uniton.
Dan, these complex configurations are still special in the way, in the sense that they give a real action?
Yeah. There's some magic there. Yeah, complex field configuration, but real action. Weird, but true. But I think there's various motivations for, if you're thinking of the path integral, you should really extend to a Lagrangian in a complex field space. And I think that's what this is telling you about.
Just to compare to something familiar. So if you suppose you take the 3 sigma model, do the same take O3 sigma model, do the same thing. The potential be what? Sine,
Sine.
which will have also instantons, and it will be quite similar story.
Yeah. Yeah, and I think for that one, if I remember right, the location of this goes off to infinity in the limit. So that the cut on the left drops out, and you only have the real field configuration. That's quite right. Yeah, good. Okay, and so there are some two-dimensional field configurations that degenerate to these. So that's really fantastic. That's resurgence in action. I'm going to speed up a bit. So I like that analysis, but it's limited. And the reason it's limited is we reduce to quantum mechanics. So how much did we really know about the full 2D QFT? That's one reason. And another reason we know that this analysis must be a bit crappy is that these instanton actions, which involve the parameters eta and zeta, are not RG invariant quantities. So I'm not sure. This location of this pole's not RG invariant. This isn't RG invariant under the flow of the eta model. So I'm not really sure what this means at a quantum level, at a truly quantum level. So, you know, the motivation should be to look at a genuine 1+1 dimensional calculation. And we didn't really use integrability. I mean, I did, because I could find the solutions of the equation of motion. But I didn't really use integrability in the way that I'm going to. Okay. So what I want to do is I want to explore exactly this theory, but in 1+1 dimensions, no reduction. And we tried this for quite some time and we gave up, either for technical reasons or for physical reasons, I'm not sure. But we can make headway on a different model, which is easier and at least as important, possibly more important, and that's the lambda theory. Okay. So I'm now going to move on to the next part of the talk, where I'm going to briefly describe the lambda theory, and then I'm going to describe some of the techniques we use to analyze it. Just a quick show of hands. How many people know what the lambda theory is? Okay, so 50% of you. So if I don't explain a bit, 50% of you are screwed. So I will explain a little bit, but a little bit quick, so everyone's a bit screwed. Okay, so this is a deformation. It's an integrable model that deforms away from a Wess-Zumino-Witten model. Okay, there's a particular construction of the integrable model, which was introduced by Svetsos, which is a bit like doing a Busher procedure, something like that. And here's the action for the lambda model. So there's a Wess-Zumino-Witten current algebra model here with level k. And then there's a deformation term, which depends on a parameter lambda, depends on some currents due to the -1 dg, and some operator which has got some adjoint action. So it's some composite operator deformation. That's what it is. To understand what this means a bit better, you could consider small perturbations. So if lambda was small, we're just deforming. We're deforming the Wess-Zumino-Witten model by two currents. For those of you who know what Wess-Zumino-Witten models are, J minus here is the wrong current, so this one acquires an anomalous dimension. It's not a marginal deformation. Or you can take lambda goes to 1, so big deformations, and you recover the principal chiral model, or in fact the non-abelian T-joule of the principal chiral model. Okay. But I think that's enough for now, is just to know it's a deformation of the Wess-Zumino-Witten model that preserves integrability. So it preserves integrability. The equations of motion have a classical lax formulation. These were slides that Thomas sprinted through today, but I think they were the same. So the classical lax for the lambda model. And actually, even better, there's an exact S matrix description. So classical is good, quantum even better. There's a quantum S matrix which can kind of be derived, actually. You can do a discretization. You get some spin chain. You can look at the excitations over the ground state of that spin chain, and you take a continuum limit, and you recover this S matrix. What you need to know about it is it's got two factors here. So this cross is actually a tensor product. One reflects some G group symmetry, and the other is like it's a kink S matrix. So it describes the scattering of kinks in a sine-Gordon theory, more or less. Okay, so this is some particular answer. And what we're going to use is yeah? Yeah, Q at root unity, maybe K plus dual Coxeter. Yeah, this is the RSOS S matrix. Okay. So what we're going to do in the last half of the talk is we're going to use this S matrix, which is an exact statement, to probe the theory. So what we're going to do is, just having the S matrix isn't enough. That's exact. I want a perturbative expansion of something. So what I'm going to do is I'm going to hit the theory, and I'm going to calculate the response to hitting the theory. So I'm going to hit the theory with some chemical potential. So there's some charge, some U1. I'm going to stick a potential for that U1, and I'm going to calculate how the free energy depends on the chemical potential. Okay, and this is a very old story, how to calculate the free energy of an integrable theory when it depends on a chemical potential. I'll often Legendre transform to the energy, so I'll switch between free energy F and its Legendre transform a couple of times in what goes on, but it's the same thing. So this goes back to the 80s. So Polyakov and Wigman showed how to calculate this quantity in terms of an integral equation. This is the TBA equation. So chi is, roughly speaking, some density of states. Chi is a density of states. B is the Fermi surface where this density goes to 0. So you have to determine B in terms of H. That's actually why this is tricky. And K is given in terms of the S matrix data. So this integral, this is a convolution with some kernel, and that kernel is the S matrix. Or more precisely, it's the derivative of the S matrix with respect to momentum or rapidity. Okay, and so if you can solve this equation, you can determine E and rho, and then you can Legendre transform and determine F. Okay, this is quite a nasty equation. Good luck solving that. And this guy did something I think is astonishing. It's one of the most technical tour de force papers I've read. Is Volin understood how to solve that integral equation to very large orders in an asymptotic expansion in 1 over B, or in H. Okay, and there were some technical tricks. I'm not going to go in much detail, but I'll just tell you what the strategy was. So instead of using chi, he worked with what's called the resolvent, and that just simplifies some equations. No big gain here, but it's nice. But he explored the equations in 2 limits. One limit is called the bulk limit. So we're always going to work at large B, but he's also going to look at large momentum. But he's going to keep the ratio of B and momentum fixed. So that's one limit. And you can just write down an ansatz based on symmetries of what this resolvent should look like. And there's a bunch of unknown numbers here, C, N, M, and K, totally unknown. You can take a different limit where you take B to infinity, but now theta minus B fixed. And you can write down a different ansatz in this limit. Again, depending on some numbers, q's, that are unknown. So we've got unknown numbers c, unknown numbers q, and a really nasty integral equation. But it turns out you don't need to solve the integral equation. It's sufficient now to take this ansatz, expand it towards the edge, and match these two expansions. And if you match these expansions, you get algebraic equations that determine all the C's and all the Q's. And you do this order by order in the chemical potential. I think this is a work of art. Getting it to actually work on a machine is quite hard, but you can, in principle, go quite high in perturbation theory. So we do this technique, and we compute 35 orders of perturbation theory. So 35 orders of a two-dimensional quantum field theory in perturbation theory. And we do it analytically. So all our results depend on kappa, which is actually k over n. And we find, eventually, the energy density has some expansion in a coupling. Little subtlety here, I do a change in what the coupling is to remove some logs. This is a nice trick, but not important. So this, we find an asymptotic expansion. Now you know the game. I'm going to say, I've got an asymptotic series. I've got to find the Borel poles. So that's what we did. Okay, we found the Borel poles. Now, because I don't have infinite orders of perturbation theory, we have to approximate this. So instead of a perfect cut, I have an accumulation of discrete poles. But you should view this accumulation of discrete poles as a cut. And again, we see this structure of alternating and non-alternating contributions. Actually, there's a bizarre feature that these red poles just disappear when kappa is an integer. That's funny. There'll be a reason for that. Okay. Divided by n. And the scattering kernel only depends on this particular ratio. And I'm in some subtraction scheme where I don't screw that up. Everything only depends on this ratio. And then it's the SUN. Lambda is gone. Lambda is not there. That's really important. The theory is, good question, the theory is gapped. Yeah? So the coupling lambda's flowing, it's becoming large, and then it's being dimensionally transmutated to generate a mass gap. And that's happening here. And then eventually, because we've divided through by rho squared, all the masses cancel. But this is in a massive theory. That's quite right. Yeah. So there's no lambda. Okay, so we found these Borel poles. So then the question is, can we guess what is the asymptotic form of this coefficients? And we, after a little bit of head scratching, we come up with some proposal for the asymptotic form that looks like the thing at the top. This is exactly what I told you at the very beginning. Alternating piece and a non-alternating piece, factorially growing, but also with some, I've been even a bit more precise. I've included some sub-leading terms and some other little bits and pieces that you need to include. And then we want to determine what this function a plus and a minus, which can depend on kappa, and little a plus and little a minus are. Yeah?
In electrodynamics, if you change the sign of its square, do you
If you take kappa to minus
do the same kappa you take kappa to minus?
kappa, I think that would be the effect of doing a summation in this axis, and you'd be worried about the ambiguity that comes from summing over here. Yeah? And indeed, there's this Freeman-Dyson point about that. Yeah, good.
There is a discrete symmetry of the sets of lambda, which is visible at the level of lambda.
Yeah.
And lambda disappears, so in the dimensional transmutation image, how it looks like this discrete symmetry?
I don't know, but this pole here is at the same place as this pole here, so I don't know if that's related to it.
It's symmetry, lambda goes to 1 over lambda or something like that. Is this one?
It might be. I'm not sure. It's a good question how that's Z2 is reflected. K goes to minus K. So right. So it probably is that this pole here and this pole here are at the same place. Probably. Thanks, Ben. Okay. So we propose some ansatz, and then what we do, we want to find the unknown functions. So here's a plot. The dots are the actual numerical data. And this was possibly one of the happiest moments of my scientific career. Because at 2:50, I said to Lucas, let's guess the form of the function. Let's guess what it is. We'll give ourselves 10 minutes to guess. And our first guess wasn't right. And our second guess, all right, there was a bit of prior, was A minus had this particular form. And blow me, look, the blue line goes straight through the dots. 8 minutes it took us to do that. That was brilliant. And then I can talk about it. And also we have a prediction for the red one as well, which is a bit less good for reasons I'm not fully understanding yet. We also know what these A plus and A minuses are. They're just 2 kappa and minus 2 kappa.
So why the product is 1 or whatever?
Why is...
Plus times A minus. Is it
No, they are to do with the S matrix. They're obtained from the S matrix in some complicated way. I'll try and explain. The product isn't actually 1, no. Okay. So now we know what the asymptotic form is, and we've got some of these subleading as well, by the way. You can actually borrow sum this exactly, not approximately. And that's what we did. We now borrow sum exactly, and we find a piece coming from the non-alternating, which has a pole or a cut starting at 2, and from the alternating has a pole or a cut starting at minus 2. Pole or cut depends on the value of kappa. And then you can do the resummation. So now we can resum this series, and we can look at the ambiguity. So we're now going to calculate the ambiguity as we resum across the red dots. And we get a purely imaginary piece with some instanton-like fugacity term, just like we saw right at the beginning of the talk, with this A plus function kicking in. Okay, so now there should be some non-perturbative sector that this talks to. Okay, I'm going to skip rather than speed up. Oh no, I'm okay. All right. So we're going to change technique now. We've done all we can with the asymptotic expansion. That bit of the story's full. But we're going to go back to the beginning, and we're going to analyze the TBA system. But we're going to do it in a different way. And this goes back to seminal works of Niedermeyer and Hasenfratz, who determined the ratio of the mass gap to the cutoff in MS bar by doing this kind of thing. It's amazing work, beautiful work, and it makes use of what's called the Wienerhopf technique. So for those of you who don't know it, what we're going to do is we're going to Fourier transform. So all our equations before were in position space, and we're now going to transform to momentum space, omega. K is the Fourier transform of the scattering kernel. And it turns out we can factorize, after taking away a delta function, we can factorize this Fourier transform into 1 over G plus times G minus. And the critical point here is that these G plus and G minus have well-defined analytic behavior. G plus is analytic up the top, G minus analytic in the lower half plane. And if you use this factorization technique, and in particular, we're going to use this combination var rho, which is the ratio of G minus and G plus. That's a particularly useful little combination that crops up. If you use this factorization technique, turn the handle quite some effort. Zamenhof claims, but doesn't give the proof in his paper, but then you do your homework, and after a week you figure out what he meant. You can find that the TBA equations can be rewritten. And this looks really rather similar to the original TBA equation in that it's an integral equation. But the main difference here is now I'm integrating between minus infinity and infinity. And that makes life all the much better. So it's for some auxiliary function u, which is determined from this equation. And if I know u, I can now determine the free energy, because the free energy just depends on u. So you just have to solve this equation. Now, there was a paper about 9 months ago by Mourinho and collaborators, and I think this one's really good. A lot of respect for this paper, because it understands where this non-perturbative ambiguity comes from. So I'm going to sketch their argument. So we have to solve this equation for u. And we have to look at this integral. And there's an integration contour here, minus infinity to infinity. So here's a picture of what's going on. Here's rho. My integration contour is the green line. And I have cuts and poles on the imaginary axis. So what we do is we contour pull, right? We contour pull this integral to both sides of the imaginary axis. But this isn't very helpful because there's a cut and there are poles at the same place. So what we do is we're going to redefine where the branch cut is in the logarithm. We're going to move the cut off the axes. That's a choice. We get to choose that. And we can either put the branch cut to the left of the imaginary axis or to the right of the imaginary axis. Okay, and then our integral comes into two bits. An integration on both sides of the cut, so that's a discontinuity integral, and a finite sum of residues, or possibly infinite sum of residues. But there's two ways of doing it. And it turns out that the two different ways of doing this contour pulling give you two different answers. So everything depends on e to the plus or minus I pi kappa, where plus is to the left and minus is to the right, or vice versa. Okay, so this equation can now be analyzed order by order in e to the b, e to the minus b, which is our non-perturbative parameter. And we get a result. So you work through the algebra, and we find a result. So we find the first couple of terms of the perturbative series. Right, so this agrees with the first term of the full thing the computer found out, but we only go up to first order. But then we find the leading non-perturbative behavior here. And as I said, this leading non-perturbative behavior is ambiguous with plus or minus I pi kappa. So if I take the difference between our prescription of going to the left and the right of the cut upstairs, what we find is an ambiguity in the imaginary part of the energy density that goes like 2i a plus this function e to the minus 2 over gamma. In fact, this expression here, which comes from the non-perturbative ambiguity at leading order, precisely matches this expression here, which came from the numerical 35 orders, resummed, processed multiple times, etc. So what we found here is a clear evidence of the same cancellation mechanism we saw right at the beginning in quantum mechanics, this BZJ cancellation, and presumably this is the start of a full trans series in which all sorts of these non-perturbative ambiguities will cancel out. Okay, so I'll just say a couple of conclusions. I won't say all of these. So just to summarize, what did we do? We used modern techniques, and as a toy model, we explored these modern techniques using this lambda model, which is interesting because it's a UV CFT completion with a dynamically generated gap in the infrared, so that's kind of cool. we saw good evidence of cancellation between perturbative and non-perturbative ambiguities, which is to say the theory is well defined. Physics is not broken. You could push this much further, of course. You could look at subleading contributions. You could look, as you said at the very beginning, Emmanuel, at higher instanton corrections or higher non-perturbative corrections. Many things you could do. One thing that we haven't done, and I don't know how to do it, is I don't know how to give a semi-classical field configuration that corresponds to these guys. I don't know what that is. So that's an interesting question. I think there was an interesting question raised by Ben this morning that I want to come back to, because, there was nothing tame at all in any of the functions I put up on the board. There were gamma functions all over the place. There were sine functions all over the place. This is a resurgent trans series. But apparently it might be physically a tame function if we calculate that free energy density. So that's a nice question relating to this morning. I'd like to know the answer to. This was all done in the context of a massive theory. But if we're doing holography, we're interested also in massless, in string theories. So it'd be interesting to know if similar analysis can be done for massless theories. Or a slightly easier question may be there are integrable deformations between two different CFTs. So maybe you can do similar resurgence analysis here. And then I think there's other more exciting ways that might have relevance for gravitational physics to look at bulk boundary integrable systems and resurgence. And maybe, rather than doing this finite chemical potential, maybe you can look at the quantum spectral curve or something like that. Okay, so lots more to be done. As anticipated, I don't think I'm going to give you part 2 of this talk, so I'm going to stop there, and thank you very much.
Okay, thanks a lot, Dan, for the nice talk. We've got plenty of time for questions, and lots of questions over there.
Yeah, so thanks for a nice talk, Dan. So just to make sure that I understood this, where you had your plot with your points, and there was a slight disagreement on the red plot.
Yeah.
So this disagreement cannot be due to like subleading non-perturbative corrections or something,
Yeah,
right?
I think it probably is.
It is.
I think it probably is due to,
Okay.
to there being some other things in this expansion. I think it probably is.
Okay.
Yeah.
All right. Okay. Good. Then.
Yeah.
I'm also happy.
That's right.
And then another question. Maybe I missed it, but at some point you mentioned your S matrix is actually a matrix, and in the rest of the talk you seem to mostly talk about a single.
Yeah, of
like,
course. I waved
kernel?
a huge thing under the carpet. So I'm turning on a particular chemical potential that selects for you certain states. So for instance, if you were doing this for the sine-Gordon theory, the chemical potential would just select out the kink-kink scattering and dispense the anti-kinks, and you would use that as your kernel.
Okay, but so then you're also working at large chemical potential or something?
Yeah, right.
Okay.
No, that's true. You are implicitly at large chemical potential. So you're making some assumption that throwing away those things doesn't impact the conclusion. That's true. And the other thing is, I'm just using the reduced TBA that has only one variable.
Yeah.
In principle, you might want to use this full TBA system with all of your fields.
But I guess for that there's no analog of Volin's analysis, right?
I think you would have to work quite hard. I'm not sure that it would be very tractable at all.
All right. Thanks a lot.
Sorry, maybe you mentioned this, but I missed what, in terms of the difference between the lambda and then the Yang-Baxter, just one side Yang-Baxter, what is the technical difference that allows you to do it for the lambda but not?
I think the physical difference is that you have this UV CFT for the lambda model.
So what if you take the Yang,
Yeah.
Yang-Baxter one side, or just squash 3-sphere
Yeah.
with the which has the UV
Yeah.
completion.
So this ansatz just doesn't work,
Okay.
and I don't know why.
Okay.
And we've tried every possible variant of ansatz that you could think of for this bulk thing, which normally involves changing this to being a square root. There's something to do with bosonic and fermionic kernels. I'm not sure if that's relevant there. Maybe you don't include this power, maybe you shift this power. You know, we've tried every permutation of ansatz that's possible, and we never made it fly, because basically this matching never worked for us. And I don't know if there's physics, or we were thick, or what, you know, I don't know. On that though, because okay, it's a bit of a niche point, but yeah, the kernel, I don't even have it. The kernel G+ for the Yang-Baxter model is really beautiful. It's a really nice, simple thing. So it looks like it should work really easily in terms of Euler beta functions, but it didn't. So we gave up.
Do we have? Maybe I have just a brief question. I probably missed it, but you mentioned when you talked about the Yang-Baxter model that you hadn't really used integrability, and
No.
you were going to use more integrability, I thought, in the lambda model, but then
In the in the
didn't see
lambda
where.
model, this is all integrability technique, of course. But back here, when we were just doing this
Right.
reduction to quantum mechanics, I didn't really care particularly about integrability at all. The only place I think it kicks in is that this is a nice, pretty potential. This has got some nice meaning in gauge theory. And to be able to identify, to solve the equations of motion, to identify these field configurations, they were easy enough equations that you could spot the solution. So the working definition of integrability is you can integrate equations. In the working definition, we used it.
so you didn't even. I mean, you didn't need to know that it was integrable.
No.
It was just
Not for this
simple enough.
analysis.
In that
Not for
sense.
this analysis, exactly.
Maybe just a comment about, you mentioned the tameness and the fact that you have lots of gammas. I mean, certainly I think Thomas mentioned this in his talk, you have ratio of gammas, so
Yeah, we've got
there's a
gamma.
good chance that this somehow makes them
I think
tame.
that's right, but I think there's something even before that point, and I was just speculating of this. Yeah, I'm going to go right to the end. Close your eyes, right. When we're doing integrable theories, we have axioms for the S matrix, okay? Factorization's the big one, that's what we're really thinking about, but there's also various analyticity properties that we place on it. But when you solve these axioms, you find that your S matrices typically do depend on gamma functions and ratios of gamma functions and stuff like that. And you do a little bit of work to remove some double poles, and there's some hand waving and stuff. But you satisfy these axioms, and you get this particular answer. Now, Thomas was saying that scattering amplitudes are tame. Therefore, S matrices really ought to be tame. So my response actually was, I wonder if these axioms imply tameness. I think that would be an interesting and precise question.
Okay, do we have some other questions? Otherwise, maybe I can just ask another very naive question about the whole Borel story. How many orders to perturbation theory would I have to compute to be able to start doing this Borel summation and
Yeah.
start seeing the non-perturbative effects?
Yeah, okay. That's a good question, actually. Obviously, the correct answer is enough. Okay. So what we don't have all the orders of perturbation theory. We only have 35. So what we do is we fake it. Okay, so we do our Borel transform series, but only including the first 35 terms. Now that is not got cuts or anything, that's just a series, that's nothing. But then we approximate that. This is just black magic. I have no idea why this works. We approximate this by the ratio of two polynomials. And that if you expand this out, you ensure that the first few terms match, but then this implies the full branch structure. This technique works with surprisingly few terms. In the 70s, people were doing this for QCD, predicting terms off 3 data points. So it's surprisingly powerful. 70s is too early. But people were doing this with very few data points. I think to get any useful accuracy for us, we found 30 orders. And let me tell you, you've not lived until you've seen a zeta 33 in your calculations. There you go.
Okay, then let's thank Dan again, and we've got a coffee break.
Do we have a break?
Yeah, we've got a 45-minute break. We'll be back in here at 4:15.
And does it also work for switching the slides?
Just before we get started, a quick practical announcement. If you want to go swimming, you don't have to send another email or something like this. Just make sure to bring your badge to the conference center venue. You can start swimming from 4 onwards. Yeah, just bring your badge. That's the important thing. They should. We just sent them everyone's name, and it'll work out that way.
Yeah. Oh, okay. I thought 45, but yeah, 55 is also good. Yeah, let's see how it goes. No, it's fine. I will have my watch in any case. So does it work? Does it work? Ah, it's off. No, it's on.
Yeah, I also can't hear you.
Now it's on.
Yeah, I think it's fine.
It's fine.
Okay, so welcome to the last session of the day. We've got Friedrich Wallach from Imperial College London telling us about exceptional algebroids and various related things.
Thank you very much for giving me the opportunity to speak here. So I would like to talk about the project that I've been working on together with Mark Bagden, Andrei Hulig, and Dan Woldram. And so the results can be found in these papers. And right, so the title is Exceptional Algebroids Embedding Tensors and Poisson-Lie Duality, and I will gradually talk about all those things. So maybe that's the first thing. So let's say that the goal of this talk and also of that work was to build a framework which would be suitable to understand several things. So for instance, some structures that appear in exceptional generalized geometry, then also consistent truncations, and also the recently introduced Poisson-Lie duality by Sakatani and Malek Thompson. So the way to do that is that I want to build a framework of using some algebroids, and I want to persuade you that that's a good and elegant way to deal with these problems. So as a first thing, let me start with a sort of crash course in exceptional generalized geometry. So first, let me say that I will work with exceptional. Oops, sorry. I will work with exceptional groups which have rank less than 7, strictly less than 7. The reason for that will be that some of the approach that I will present, it's sort of there is some problem in extending it beyond, but it's a doable thing, but it's still we've dealt it only up to that rank. Some interesting things happen if you go to 7 and beyond, and we are working on that, and you can ask that later, or I will comment on it at the end. But so for now, I will focus on the case up to 7, without 7, so up to 6. So what is happening there is that if you are working with 11-dimensional supergravity or type 2 supergravity, then the symmetries of the theory and the dynamics and the dualities can be neatly captured and encapsulated in terms of some bundles with some extra structure. So for instance, more precisely, if you consider this reduction to n dimensions of 11D supergravity or to n-1 dimensions, then the symmetries of the theory, they are governed in the first case by sections of this bundle. So basically you have vector fields which generate diffeomorphisms, you have 2 forms and you have 5 forms. And if you put these things together like this, then there is a natural action on the exceptional group. So the exceptional group, this notation, if you're not familiar with it, it means that this is the split real form of the complex exceptional Lie algebra of rank n. So basically, yeah, okay. So it's just some abstract thing, and the symmetries of the theory are governed by sections of this, and the algebra of these symmetries can be described using these brackets you can see here. So you have a vector field, 2 form, 5 form. And another such thing, and then you can build an expression which uses only some natural differential geometric operations, such as Lie derivatives, wedges, D's, insertions, etc. And the bracket has some nice properties, and yeah. And then you can do the same thing for type 2a and 2b, which is rather surprising to some extent. So you can the bundle is now more complicated. So it has more summands, you have T, you have vector fields, you have 1 forms, you have 5 forms, and you have some other stuff which is either even or odd differential forms depending on whether it's type 2A or 2B. And again, the algebra of these symmetries is captured by some bracket which I'm not writing down because it's rather long and not that enlightening, but it's just as before, it's built out of these natural operations. And this bundle, again, lies in a representation of or the fibers of this bundle are well, there is the exceptional group acting on them. It's actually the same representation, but it's seen in a different decomposition. So, okay, so far for this, I was talking about symmetries, and then apart from symmetries, this exceptional geometry allows you to talk about bosonic fields. So the bosonic field content of the theory, of this reduced theory, is basically can be neatly encoded by saying that it's nothing else but a reduction of the structure group from this exceptional group down to its maximally compact subgroup. So K stands for maximally compact. So if you know about the reductions of the structure group, then the same thing happens if you study, say, GR, where you have metric, and okay, if you assume that it's Euclidean for simplicity, then or Riemannian, then Riemannian metric is the same as reducing the structure group from GLN to its maximally compact subgroup, which is ON. So this is a precise analog of that statement. And just as analogously, you can build some curvature tensors out of these generalized metrics, and vanishing of these tensors will correspond to the fact that these fields, the bosonic fields, are on shell. So the story very neatly generalizes the usual story of Einstein-Hilbert action and of GR in this exceptional setup. Now, to be more concrete, and there is another interesting thing that one can do, and that is to study maximally supersymmetric consistent truncations. So we heard about consistent truncations a little bit before. So those are physically interesting things. And what was shown in this paper by Lee, Strickland, Constable, and Waldram is that if you require maximal supersymmetry for these truncations, then you get that this is basically the same as having what is called Leibniz parallelizations. So Leibniz parallelizations, to break it down, it means that you have a manifold, M, some space, and over it you take this bundle, or this bundle, but depending on which theory you're interested in, and you demand that there exists a global frame such that if you take the bracket, then the bracket closes on this frame with constant coefficients. Okay, so what is non-trivial here is that you want the frame to be global, you want it to be compatible with the exceptional group, and you want that the structure coefficients are actually constant. So this is a very strong constraint. So for instance, if you would have kind of a primitive version of this story where you would throw out everything and you would just leave with the tangent bundle and with the lead derivative, with the commutator of vector fields, then if you want that such a thing is parallelizable, then basically means that the manifold has to be a group or a discrete quotient of a group. So this is a very, very constraining condition. And therefore, one natural question that you can ask is, what are such possible spaces that admit these parallelizations? And that's kind of like a guiding theme in this presentation, and I want to show you that how there is like an elegant way to kind of settle to some extent this problem if you embed it in a slightly larger framework of algebroids. But before talking all of that, I will pass to some simpler setup, and I will demonstrate the thing in the simpler setup, and then I will just tell you the result in this case. So in the simpler setup is the one of generalized geometry, where instead of that strange bundle before, you have just the sum of the tangent and cotangent bundle, and instead of the exceptional group acting on it, you have the ONN group. So such a combination, it has a natural canonical pairing, canonical inner product, which is given by pairing of vectors and covectors, and the group that preserves it is ONN. And again, just as before, you can use this in string theory. If you can see this as encoding the symmetries of the NS-NS sector, and the algebra of these symmetries is governed by this bracket here. So here, note that here I put an extra piece here given by some chosen closed tree form. Okay, so in this context, you can ask the same question. You can ask, like, okay, can you define Leibniz parallelization in the same way? So you want to have a global frame on which the bracket closes, and you want it to be compatible with the group. So in this case, it means it's orthonormal. And okay, so the question is now, what are the spaces which admit such a thing? Can we classify them? Can we find them? What are they? This is a rather simple question with like an answer to that is not difficult, but I want it to be like a guiding principle for the exceptional story later. So, okay, so a particularly elegant way to answer such question is now to pass to a slightly more general setup of algebroids. So let me talk briefly about courant algebroids. So the proper definition is that it's a mathematical structure which consists of some set of data satisfying some axioms. So there is a vector bundle which has a bracket, which has a pairing with inner product on the fibers, and it has a certain map called the anchor map, which goes from the algebroid, from the vector bundle to the tangent bundle. And there is a bunch of compatibility conditions which I'm not listing, because if you haven't seen them before, they are not that enlightening, and if you have seen them before, then you know what they are. So you can look them up. The point is that there are certain somehow more or less natural conditions that you can put on this data. And but perhaps more important than the definition, let me talk about the examples. So as I said, this is to be seen as a slight generalization of this generalized tangent bundle from before. This thing. So indeed, this thing is an example. If you take this to be your bundle, you take the bracket from before as your bracket, you take the pairing, the dimensions to be the pairing, and you take the anchor map to be simply the projection onto the first vector. Okay, so this is kind of simple. What is perhaps a little bit more extreme example is that if you take the definition and if you restrict to the case where this M is a point, in that case the anchor map is necessarily 0, so all is left is a vector bundle over a point, which is a vector space, and a bracket, and a pairing. And if you look down at these conditions, which I didn't write, you will see that the condition is that the current algebra is simply a Lie algebra with an invariant pairing. Such a thing is sometimes called quadratic Lie algebra. Okay, so those are kind of the two most important, at least for the present context, examples of such structures. And now the crucial point is this theorem of Pavlov-Shevera, which shows that there is actually a neat way how to recognize when a given current algebroid can be put into a form of a generalized tangent bundle. And so the answer is as follows. So you can first of all you can show from this definition that to any current algebroid there is a natural associated sequence which looks like this, where the maps are given by the anchor map and its transpose. And it follows from the axioms that this is actually a complex. So if you compose two subsequent arrows, you always get 0. And now what Pavlov proved is that if you have a given current algebroid can be recast in this form, if and only if this sequence is actually exact. So exactness means that the kernel of an arrow is always the image of the previous arrow. Or in other words, there is no cohomology. This is like a one-to-one thing, and the usefulness of this theorem lies in the fact that there are many ways to produce current algebroids, and sometimes, and usually it's not obvious that whether those algebroids are or are not of this form. It's not obvious on the nose, and that's actually why the story is interesting, because there are ways to produce current algebroids, and you can show that they are actually exact, which means that they are of this form, and you can relate them to whatever the stringy purposes you have. And if you do that, you will notice that the formulas are kind of horrible and complicated if you want to do it explicitly. Yes, please.
Is your generalized bundle here always an exact direct sum, or are you just simplifying life? Is it always direct sum T and
Yeah.
T star M, or
Yeah, but here, by generalized tangent bundle, I mean that it's...
locally?
No, here I mean globally.
Okay.
I mean, this example, there will be a more subtle thing coming with the exceptional case, but in this case, here I mean globally.
Okay.
That's a good question, thank you. Okay, so we have the definition, we see the two examples, and we see an abstract way how to characterize the first example. Okay, now we can return back to the question of what are the manifolds that admit such a global orthonormal frame of the current algebroid, of the generalized tangent bundle. And so from this theorem, we see that basically we can rephrase the condition as searching for Leibniz parallelizable exact current algebroids, because we know that they are the same as exceptional generalized tangent bundles. And now it becomes slightly easier, actually. So suppose that, let us see what does, if we have such a structure, what it breaks down to, what are the data that determine it. So suppose that we start with a current algebroid, which is exact, and is parallelizable, and also assume for simplicity that the base is compact. Now, one direct consequence of such parallelizability is that you can write down this vector bundle as a product of the base with some vector space, because in particular, parallelizable means that you have a global frame, so you can trivialize the bundle. And another consequence of the definition of parallelizability is that you will actually get a well-defined bracket on this vector space. So it becomes a current algebroid over a point. So it inherits the bracket, it inherits the pairing, and it becomes this thing itself a Courant algebroid over point, which we know is the same as a quadratic Lie algebra. So Lie algebra with an invariant pairing. Okay, so we have some Lie algebra. Now, let's go back to the anchor map. So the anchor map, if you remember, the anchor map was a map from the vector bundle to the tangent bundle. So in this case, since our vector bundle is just product, the anchor map has this form. Now, if you look at it, this is basically saying that this Lie algebra acts on the manifold, because if you pick an element of the Lie algebra D, you pick a point on M, then this map gives you a vector at that point, which tells you like what is the infinitesimal action of the group if you would integrate it to a group. So yeah, so it gives you what is called an action of a Lie algebra. But now we return back to the fact that this is exact. Now, since it is exact, in particular, if I go back, exactness means that in particular the anchor map is surjective. So in this context, we have a surjective or rather transitive action of a Lie algebra, and it is well known that if you have such a thing, then you can, and the manifold is compact, then you can actually write it as a quotient of that corresponding group. So this D is a group corresponding to Lie algebra D, modulo some subalgebra. So you can see it as a coset space. So okay, so if we go back, it basically we started with a parallelizable exact Courant algebroid, and you see that it basically corresponds to some pair of Lie algebras, and actually you can recover it fully from this pair. But now this pair cannot be arbitrary, because again, if we go back, exact Courant algebroids are those that look like this, basically by the Powell's theorem, and those ones have the special property that if you look at the anchor of the row map, that the anchor of the row map is given by this guy here, by the cotangent bundle. And the cotangent bundle is half-dimensional with respect to the whole thing. It's half rank. And also it's isotropic. And so it's half-dimensional isotropic. Such things are called Lagrangian. So you see that the kernel of the anchor map is actually Lagrangian. And because this is simply because it is exact. But if we go to our description in terms of this thing, then you see that the kernel of the anchor map, so the anchor map is just the action of this Lie algebra D on this quotient. And the kernel is given precisely by the Lie algebra H. So it has to be Lagrangian. So to summarize, after this painful discussion, so there was if we start with a parallelizable exact Courant algebroid, then we can create, then this always gives rise to a pair of a Lie algebra, which is quadratic, it has a pairing, and a Lagrangian subalgebra, which means maximally isotropic. And such a thing is called Manin pair. And okay, and now it is you can search in the literature about Courant algebras, and you will find that this is actually one-to-one. It goes also in the other way. Okay, so I showed it this way. The other way it's slightly more subtle, but not very much. And actually, to show it the other way around, so that Manin pair induces a parallelizable exact Courant algebroid. The way you do it is actually that you start with this Manin pair. You kind of try to go back, you go to this space, you build some algebroid over it, and then you have to check that it is actually Courant. And to do that, it's kind of easy to do it from this abstract definition. So in this way, you kind of circumvent the need to working with this T plus T star to this direct sum. Instead, you work with the concept abstractly, and this makes the calculations kind of trivial. So this is why it's useful from this aspect to use these things. Okay, so we have a correspondence between these Leibniz parallelizations and Manin pairs. So we basically sort of answered the question before. But now it's actually a good time to pause at this point and to realize that we also have a link that one can also, in this language, give some insight into Poisson-Leyti duality, introduced by Klimčík and Ševera in the 90s. So what I will talk about is only a the simplest setup. So the story is much more general, but in its simplest disguise, you can say, and using this framework, that Poisson-Leyti duality corresponds to basically having this pair, but having H and D, but having also another H. So having the same D, but two possible Lagrangian subalgebras. And the reason, or you can have more, you can have 3, infinitely many, it doesn't matter, but the point is that you have more than one. And so suppose that you have 2 such Lagrangian subalgebras, then what you can do, by the previous discussion, you can create a parallelizable exact Courant algebroid, in other words, parallelizable generalized tangent bundle over these 2 quotient spaces. And now the claim is that if you put some dynamics on them, if you put some dynamical quantity, some generalized metric on this Lie algebra D, then it carries over to generalized metrics here and here. And if you use that as a target of sigma models, then you can show that these sigma models are dual in some well-defined sense. So this is one way to say what it is. So from this perspective of courant algebroids, in this context, it corresponds to basically picking up two Manin pairs for the same Lie algebra. And in a special case, if these two Lie algebras are complementary, in general they don't have to be, but if they are, then at least locally you have that you can identify the quotient with the other group and this other quotient with the first group, so that your dual spacetimes, stringy spacetimes, are given by these by these groups, which in this case go under the name Poisson-Lie groups because they carry a compatible Poisson structure, as was I think discussed today already by Chris. And yeah, so this is where the name comes from, I believe. So, okay, so this so far this was the generalized geometric case. So you see that you could break it down to basically this statement. And now let me go back to this exceptional story. It seems that I will finish earlier. So if you have any questions, then go ahead. Yes.
Yeah, so in this story, how do you go between algebra and group by exponentiation? Do you have to worry about discrete factors?
So, I would worry only here. I think so. So, if as far as this quotient goes, there everything is works without any problems. The problem is if you want to write like explicit coordinate expression or something like this. If you want to, for instance, work on a group, then you have to make this identification. So, in doing this identification, if you want to really see that it as living on these groups, then there might be some possible problems with like some global issues. But if you don't do that, I mean, if you don't consider the special case, even in general, it's like working on these quotients makes it perfectly well defined. And even better, actually, these courant algebroids, that's maybe a thing I should have said, it kind of allows you naturally to, like, they bring in naturally this three-form flux, like a non-exact version of that. So you automatically get some, like like you can work with non-exact three fluxes. They just come in automatically in the game. Actually, generically, I think they come. That's what happens when you work on these quotients. And if you want to make a identification with the group, then yeah, you have to be more careful. I hope that's what you were asking. Okay. Yep.
Sorry, I have a question. The anchor map can be understood as a kind of generalized field line or something like that, because it has the structure of one curve index. If you put indices over this map, it has kind of one curve index and one kind of flat one. It's a kind of relation between, or an interpretation of the anchor map as a field line in the generalized geometry.
I usually don't think of it that way. So one thing is that usually it's not. I mean, so Philbine usually want it to be an isomorphism. And in this case, this thing is quite far from that because in this case, for instance, it has a kernel given by this bit. But I mean. I don't know if it's fruitful to think of it as a Philbine. Maybe it kind of makes contact with this abstract bundle and with what is happening on the tangent space, but or are you asking more in like relation to Poisson-Lie duality and?
Because you have a generalized metric over there.
Right. Right. I see.
We can discuss later. Don't you worry.
Okay. But yeah, at least like from a general perspective, like if written abstractly, there is no clear. I mean, from this perspective, it's maybe not fruitful. But I think I know what you mean, and yeah, maybe in a sense. Okay. Okay, very good. So now if we want to go to the exceptional version of the story, so this is the work that we've done. Basically, the ingredients for that can be found in these works. At least that's where we drew our inspiration. So basically, the idea is that you can build a more general concept than courant algebroid, and this concept stands on some choice of several things, and those things are a group and its two representations. So in the ONN case, in the courant algebroid case, the group was ONN, and this representation E was the vector representation in which the generalized tangent space was. And this N was just one-dimensional space, real numbers. So in exceptional geometry, you want to generalize this to some more general thing, and namely you take some, but it's, okay. So for those of you who know about tensor hierarchy, then I think those 2 bits are basically the first 2 bits in tensor hierarchy, so this is where you get the representations from. But like in general, to write down the definition that I will write on the next slide, is that what you need is just a group, and 2 of it, 2 is representations, and you want that there are certain maps between, there are certain symmetric maps between E and N and the duals. So in a sense, you want to see this N as being a generalization of inner product. It's like you have like a couple of inner products. And more concretely, for these exceptional groups, the representation corresponds, the E representation is the fundamental corresponding to the leftmost node, and N is the one corresponding to the rightmost node, if you write them like this. Okay, here is a little, okay, whatever. Yeah, and because the groups we work with are all simple and nice, then basically, I mean, these 2 maps, they come out automatically. They are just projections down to sub-representations. Okay, up to a scaling. Okay, so this is kind of the data that we need to fix. So we fix G to be this group, and we fix these 2 representations E and N, and now we can write down the definition. So if you remember the definition of courant algebroid, then this is basically, I just copied it and changed a few words. So exceptional algebroid, or okay, one can also call it algebroid for short, is a structure given by a vector bundle, a bracket, an anchor map, and instead of an inner product that we had in the current case, now we have a G structure. And since we have a G structure, then it means that you have a principal G bundle behind it, and you can construct the associated bundle corresponding to the N representation. So what I'm saying is that if you have these things, and for free you get a second bundle which corresponds to this N representation. And so here I'm making a little bit of an abusive notation because I want that these E and N bundles, they transform in these E and N representations. Okay, so you can write down. Okay, if I write like this, it looks very straightforward. There is a little bit of subtlety in doing it, but yeah, we figured it out, and it's not a big deal. So basically, you can generalize the definition to this exceptional case. But now, what kind of makes us sure that this definition is the right one is the following rather non-trivial fact, that there is a way similar to Shevera's theorem about classification of exact current algebroids. There is a similar way how one can recognize when a given exceptional algebroid has the form of one of these things that I had at the beginning. This one or this one, because those are the ones that play the role of generalized tangent bundles. So kind of the first result is that there, which we proved in this works, is that there exists a certain natural sequence following from these axioms. It looks like this. It's again, there is the tangent bundle, there is the E bundle, but there is something slightly maybe new. And yeah, so you have a different sequence, and the claim is again that from the axioms it follows that this thing is a chain complex. So if you compose the 2 subsequent maps, you get 0. Okay, so this you can show, this is fairly straightforward. What is less straightforward is actually this theorem that we proved, that actually if you require that this is in fact an exact sequence. So exactness, so note this subtlety that now we don't have like 0 on the left. So exactness now means exactness in here and in here. Okay, so basically it means the row is surjective, and in that kernel row is image of this. So okay, so if you have an algebroid or exceptional algebroid which is exact, then you have basically 2 cases. One is that the dimension of the base is the same, is n is the rank of the exceptional group, or it is n minus 1. And the claim is that if this is so, then locally, it's important, you can identify the exceptional algebroid with the exceptional tangent bundle for M theory or for type 2b theory. So those ones that we had at the beginning. These rather long expressions, together with the bracket and everything. There is a similar thing for 2a, which is more subtle, because 2a is in a sense non-maximal theory from this perspective. So basically, but you can still recover it if you require like sort of minimally non-exact theory. So you don't want that the cohomology is 0 and 0 as you would in the exact case, but instead you want that this is 0-dimensional and this is 1-dimensional. And then you can show, and this is a rather messy calculation, but the result is elegant. It just says that you recover the 2a theoretic.
Friedrich,
Yes?
I have a
Sorry.
small question. So for Cheveray's result, it's also a classification.
Sorry, I don't...
So for the normal exact case, it's also a classification result. So here also you have a classification in terms of fluxes, because there in the normal exact case it's classified by 3 form fluxes.
Yes, okay, very good. So thank you. Yes, so yeah, right. So in Pavlov's case, so in the current algebraic case, actually yes. So one statement is that the one I said, that if you can, a current algebroid can be written in this form if and only if the sequence is exact. But actually, you can go further and you can actually show that such possible exact current algebroids are classified by the third cohomology class of the manifold, because for this because you have presence of this H flux here, and so if you are given an abstract current algebroid satisfying that this is exact, then you can always put it in a form like this for some H, but this form is non-unique. You can also, using some different choices, you can identify it with different H's in the same cohomology class. So basically, it only depends on the cohomology class. And in here it's more complicated. So the easiest way to say it precisely is that if this is true, then locally, so basically there are kind of like two. Sorry, if it's exact, then there are two possible normal forms in which you can put the algebroid locally. You can either have that thing or that thing. You can still twist them somehow. If you're interested in the global thing, you can still do some twists. But the gluing is kind of more complicated in this case, and it's, to me, it's not even clear that globally you can if you have an exact exceptional algebroid, that you can globally identify it with anything like this. Already that is not clear to me that that's. I mean, as a bundle, not talking about the bracket. Already as a bundle, it's not clear to me that you can write it globally like this. In current algebroid case, you can, because some things are simpler there, and in some sense, it's some sort of abelian version of the story. But this exceptional story is more interesting, perhaps. So I don't want to. So I'm not claiming anything about the global thing. I will tell you about twist on the next slide. But it still doesn't answer the question about the global classification. Is still a little one step further in difficulty. Okay, there is maybe a caveat here, not caveat, actually a beautiful thing that actually I said that if it's exact, then you have these two. You can either put it locally into this form or this form. But if it's in these two AKs, there are actually some local moduli that you cannot get rid of because you have some scalar deformations. Possible massless deformations of the theory, so I will talk about it on the next slide. So here, in this case, actually, locally, the form of the algebra is not unique, but it depends on. There is a 1 or 2-dimensional degree of freedom left. So let me go into that. So fluxes. So if you go through the story, then you see, by the way, that it gets progressively more and more complex. So in M-theory case. Sorry, I should have said that the way to prove this is basically to go in the same way as for current algebroids. You kind of build something and then you have to show it satisfies these axioms. So that's where you kind of heavily use the fact that you are working with some abstract concepts like this. And in the course of that proof, you actually also find out what the possible twists are. So let me give them here. So for the M-theory case, you have a possible twist by 1 form and 4 form. So just an emphasis, remember that we are working with exceptional groups of rank up to 6, including 6. So the manifold, in this case, it's 6-dimensional at most, and in type 2, it's at most 5-dimensional. So that's why you don't have the 7-form flux and these things. So yeah, but the remaining fluxes are a 1-form flux and a 4-form flux. This one is related to the 3-form in M-theory, and this one is related to the fact that we are working with warped compactifications. So those are kind of the things that appear naturally in the context of this type of geometry. So this is kind of related to the field strength of the warp factor. And there is some Bianchis that this has to satisfy. What is rather more interesting to me is the 2B case, where where the formalism kind of enforces or shows that the fields naturally or the twists naturally organize into some objects like this, which maybe it's known, but to me it was a surprise that it kind of very neatly organized. The twists organize into a flat flat GL2 connection, a covariantly constant doublet of spinor of 3 forms, and a covariantly constant 5 form, but that condition is not here because it's 5-dimensional at most, the manifold. But it's kind of curious that it organizes like this. So if you're interested in how this relates to the scalar degrees of freedom of 2B, then you can ask me. But anyway, in the 2A case, it's even more complicated because there is less structure to work with, and the case is not maximal. It's not exact, but it's minimally non-exact. So the story is more complicated, but in particular, the interesting thing is that you have 2 possible zero-form fluxes, which satisfy the condition that their product is 0. So one of them has to be 0 at least. If you have like a compact connected manifold, then basically at least one of them is 0. And these correspond to deformations. One of them is the Romance mass, and the other one is the parameter coming from this paper, I believe. I don't remember which one is which. Maybe you can infer it from here. But you see that there is a bunch of things. So actually, maybe I can say a little bit about, like, when you're trying to prove this thing, that exactness of this sequence or minimal non-exactness implies something and something, basically the thing you do is that you build this algebroid, and then you are checking the conditions, and then you discover that actually locally you have the possibility of these twists, and then what you do, you are trying to use the gauge freedom to kill those twists. And even though I'm not writing the gauge transformations, it's kind of a funny exercise to check that you can one by one eliminate them until you, in this case, end up with 0 flux, here with 0 flux, and here with one of these two guys at the end. Okay, so this is the story of the twists, and now let me I think talk about, oh yeah, the parallelizations, the thing I promised. So now without further elaborations, I can tell you what the result is. So I should say that the result of this part, it kind of parallels a result obtained by Gianluca Inverso in 2017, where he used a language, like a very different type of language for obtaining basically these kind of results. But yeah, so in a sense, this part of the work can be seen maybe as a simplification and maybe a slight refinement of his results. So, but what the result is, so the result stated again elegantly in terms of these algebroids is that these exact parallelizable algebroids, or in other words, maximally supersymmetry consistent truncations, they correspond not to Manin pairs, but something that you can call exceptional Manin pairs. And so they are again given by a pair of 2 things. So there is like, instead of a Lie algebra, you get a algebroid, exceptional algebroid over a point. So this is essentially, if you think about it for a second, this is the embedding tensor, like literally, or well, structure of an algebroid over a point is really the same. This encodes the embedding tensor, and instead of a Lagrangian subalgebra, you have a coisotropic subalgebra, which is a slightly more general thing. And the proper definition of that, if you want, is that it means that if you take the annihilator of V, so I'm defining what coisotropy means. So you take the annihilator of V. So annihilator is a subspace of the dual consisting of covectors which kill your space V. Okay, so this is a annihilator. And if you take any 2 elements in the annihilator and use this map here, then you demand that this is 0. So that's the condition of coisotropy. It's kind of dual to the notion of isotropy. Whatever, it's some condition. And on top of that, there is some 2 mild conditions that are kind of not present in the current case because they are actually automatically satisfied. So one of them says that this algebroid over a point is now not necessarily a Lie algebra, but at least you know that the symmetric part of the bracket has to be inside this subalgebra. So this coisotropic subalgebra has to contain all the bad stuff, all these things of this form. And secondly, and perhaps more intriguingly, there is a certain trace condition that looks as follows. And yeah, there is some constants in the game. And intriguingly, this condition is always satisfied in the M-theory case. I don't know about any direct way to prove that, but it follows from this framework that it's satisfied. Okay, but those are just mild conditions. And actually, in examples that the people usually study, I mean, you won't usually, if you have some unimodular stuff, then this is kind of, traces of adds are usually 0. So this is not a big restriction. But now you can also look back, and you can try to reformulate the Poisson-Liu duality in this language. So in this language, it corresponds, as before with Poisson-Liu duality, it corresponds to fixing E, but taking different V's inside. And actually, the framework I'd automatically, again, using this beauty of these algebroids and of the compatibility of these structures, you can show that actually this is automatically compatible with supergravity equations. That follows kind of semi-automatically. You only need to do a little bit of check. Right, so that's what we did in the first paper. Okay. So yeah, now let me go to examples. So kind of the simplest class of examples that we have. So first of all, I should say, okay, so if I want to give you an example of such a parallelization of our Poisson-Liu duality, basically at this stage it just suffices to give you a pair of these two things. So space with a bracket, this algebroid, and a coisotropic subalgebra of that. So the simplest case is if you take the bracket to be 0. So if you take the big space to be abelian, and therefore any subspace is a subalgebra. So the only condition, this is trivial, this is trivial. Only condition is that it needs to be coisotropic. So if you have a subspace and a coisotropic subspace of that, then this leads to an example always. And then the space that you will get, this parallelizable space, will be a torus. And now different choices of this subspace are different choices of coisotropic subspaces, if I now want to make a connection with the duality. So different choices of subspaces are related by the action of the exceptional group, and those considered to the kind of dual tori, or U-dual tori. So this is the usual U-duality. Yeah, so that's the first example. And in the second example, this is kind of a backwards going example. So we already know it's easy to see that any group is automatically a Leibniz parallelizable manifold. So this corresponds to Church-Schwartz reductions, I believe. But yeah, if you want to cast it in this form, then you can identify what is this exceptional Manin pair, and so it just consists of this algebra and this subalgebra. Okay, this is kind of half trivial, but I'm just saying that you can embed this story of Church-Schwartz reductions or parallelization, consistent truncations on groups into this framework. And what is maybe more interesting is that you can also see what the generalized Young-Baxter deformations are in this case. So they just correspond to the fact that you fix this E, but you deform this V such that it stays transverse to the first bit. And yeah, and then the condition for such thing is the condition for this new subspace to be still a subalgebra is the Young-Baxter equation. So the story embeds like this. Note that in both of these cases, you have that so you have this E space and you have V sitting inside it, and an actual complement to this V is this K here. So in this case, and also the one above, because it's a special case, you see that this V has a natural complement which is a Lie algebra. So this relates to the thing that Chris was saying before. I think that you can have this, like the first batch of these generators of the exceptional Greenfield double. They don't have to form necessarily a Lie algebra. In this case, they do, but in general they don't. I mean, in here you don't have such a. I mean, yeah. Here the only thing you want is that you have this coisotropic subalgebra. So it's dual. Its complement may or may not be a subalgebra, and in fact, in the next examples, it will not be. So let me pass to the more interesting examples. So you can recover spheres. This is as explained in this paper. In our framework, in this framework, it just amounts to saying that you take the pair of SO5 and SO4. Okay, so SO4 is a subalgebra of SO5. But what is okay? That's simple. But what is kind of non-trivial is that it is a coisotropic subalgebra. That's kind of it's kind of the only pair of Lie algebras where this happens that I know. That's yeah. I can be more explicit if someone wants, but yeah. In this case, it just so happens that this is a coisotropic subalgebra. The other conditions are trivially satisfied, and the parallelization that you get is the one on a 4 sphere.
Friedrich?
Yes?
You're always thinking compact here, I guess, right? When you say the only example.
Uh,
Because you could do
yes.
trivial other examples, but
Right.
taking non-compact real forms.
Yeah, I guess I meant compact. Thank you. Yes. Yeah. Thank you. Right. So yeah, this gives an M-theoretic parallelization. So you get an exceptional tangent bundle in the M-theory sense over this, and you get a parallelization. So you can do consistent truncations on a 4-sphere. A slightly more complicated example is you can recover the 5-sphere in the type 2b case if you take this kind of algebra. So the notation, by this notation I mean that you have this space SO6 plus 6 plus 6, and now the bracket on this thing, this exceptional algebraic bracket on it, is given such that, first of all, this is a subalgebra, so a bracket of 2 guys in here is the SO6 bracket. Bracket of this and this is just the action of SO6 on this representation space. But on the other hand, if you take bracket with anything in here, that's 0. Okay, so this is central, this is left central. So you see that the bracket here is not skew symmetric, because if you take the cross bracket, then it's not skew symmetric, because bracket of this and this lies in this, but bracket of this and this is 0. So this is not a Lie algebra in the usual sense, I mean, in any sense. But still, if you take that, and if you take this to be your subspace, then you can again check that this is coisotropic, and then hence if you integrate it to groups, then you get a 5-sphere as a quotient. And okay, so in these cases, unfortunately, there is not much of a duality going on, but if you perform some contraction, if you degenerate this example, the second one, if you degenerate the group, the algebra SO6 to SO5, semi-direct product with 5, it's called a Wigner contraction or Wigner-Inonu contraction, and you keep the rest untouched, then this thing will admit to two interesting coisotropic subalgebras, one of them given by SO4 semi-direct product 4, and the other one is by SO5. And the product and the quotients will give you a 4-sphere times R or R5, and those are dual to each other by the previous abstract nonsense. And they are both 2B parallelizable. Unfortunately, they are not compact, but okay, what can one do? If you want a compact example, still perfect. Still rather maybe a simple hands-on example is that if you take the similar thing, you take just SU2 plus 3, meaning again that this 3 is central. So bracket with anything in 3 is 0, and the cross bracket is given by the bracket of something in here, and in here lens in 3. So this is the algebra, and the coisotropic subalgebra. You have 2 choices. You can choose either 3, or you can choose U1 plus 3, and one of them results in a 3-sphere, and the other one results in a 2-sphere. And they are, by this argumentation, they are Poisson Liu dual. And one of them is M-theoretic, and the other one is 2A theoretic. Okay, so much for the examples. And yeah.
Friedrich, can I just ask a question here?
Yes, please.
As you mentioned, when you discussed the Poisson T duality there, with the generalized metric, you can construct a sigma model where you can define really a notion of duality. Do you have any idea what to construct here so that Poisson Liu duality is made manifest in some?
So no, not in terms of sigma model, that I don't know, but in terms of supergravity, you can do that. That's what. Yeah. But I don't have anything intelligent to say about this and how this relates to Poisson to sigma models, unfortunately.
What is the condition that if you take 2 coisotropic V's and they give the same solution of supergravity after after diffeomorphism? Is there some condition like that?
Well, yeah, it may so happen that they give the same space. Like for instance, in this kind of half-trivial case, when you have a torus, you always get, if you take different choices, you always get different tori. But it becomes interesting if you put some generalized metric on it, because then the resulting torus, if you identify all quotients with some given torus, then the generalized metrics will be different. So in terms of space, I mean, well, there is the obvious condition that if you have such a coisotropic subalgebra and you act with the adjoint action on it, then you will get a space which is the same. But in general, I don't think there is a general condition to determine when 2 such things produce the same thing, at least as far as I know. Okay, so yeah, that's it. So I can tell you what more can be done with this. So obviously there is a problem of higher rank. Maybe at this stage I can say, so the problem with this E7 case is that one of the axioms, which I didn't write, is no longer satisfied as it is written. So the thing is that so if you know about Courant algebroids, then there is a axiom which says that the symmetric part of the bracket is governed by the inner product of the bracket on the Courant algebroid, and there is an analogous condition here, but that condition is not true in the E7 case because of some, well, because it's not true. Stuff gets kind of more complicated. So there are other things that you can say. There is a framework in which you can generalize this thing, but then you have to be careful and you have to check whether that more general framework whether you can still recover your exceptional tangent bundles from this condition, because that's kind of crucial to the story. That you want, like the idea was not to build any generalization. I mean, if you want to have any generalization, then you can talk about Leibniz algebroids. They are very general and they encode all of these things, but they are too general. The thing is that you want to have notion which is strict enough so that you can recover from the exactness of this sequence the tangent bundle, the exceptional tangent bundle. So in the E7 case, this is a work in progress, but yeah, so how to fit it in this particular framework. And right, and then you can talk about global classification, as we briefly touched before. And another particularly interesting thing is to deal with non-maximally supersymmetric consistent truncations, because those, as you see here, these maximally supersymmetric consistent truncations, like they correspond to these exceptional Manin pairs, and this is a super strong condition. So as you saw, the examples are not too numerous, but in the case of non-maximally supersymmetric consistent truncation, story is much more. There is lots more interesting geometry flowing around, so that's another thing to do. And then you have usual stuff. You can encode, try to put in fermions. You can try to go away from exceptional groups towards some like more general triples of this data. That's also an interesting thing, and so on. So yeah, that's all from me. Thank you very much for your attention.
Thanks a lot, Friedrich. We've got, again, plenty of time for questions.
So it's related to Eric's comment in the middle of the talk.
Sorry?
It's related to Eric's question. So I was wondering, how you can derive the geometry related to these theories. So if you have so Chris showed us some generalized field line in his talk. So I was wondering in this language, how we can extract like a metric and the tree form and stuff like that.
Right. Okay, that's a good question. So in the Courant algebroid case, so the way that I presented it here is kind of, I find it particularly elegant because you don't have, well, it's kind of abstract. The point is that if you want to perform some, okay. So actually, the difficulty or kind of the non-triviality comes from this statement, because the way you produce these, how to say that? So kind of the reason Poissonnet duality gives such relatively complex examples, like that you can get some pretty wild and interesting spaces, is in a sense that there are two different descriptions of a Courant algebroid over this quotient. One of them is the one which is simply T plus T star. That's the one you weren't explicitly for string theory. But there is another one which comes out naturally if you do follow this construction, and that one is kind of that's a picture of where you have a trivial vector bundle over this. And those two are equivalent, but they are non-trivial. There is like the equivalence is kind of non-trivial. So if you want to really relate follow this construction and at the end recover explicitly what the generalized metric looks like, you have to follow that isomorphism between those two things. And there are ways, there are concrete ways which I should probably remember and maybe I can recall. But so in the Courant case, this is possible, and there is like a well-defined recipe how you can recover that. But it requires some choices. That's important because that's one of the reasons why the story is so interesting. That there is no canonical choice. If there would be a canonical choice, it would mean that the story that you get at the end would be kind of simple. But anyway, sorry, I'm getting maybe too far. So in the current, so the answer will be that in the current case you have a way of like recovering these things, and in the exceptional case there should also be one, but I didn't think of it so far. But you should be able to do that. Sorry for a roundabout way to say that.
So maybe this is related. The bivector is telling you how to twist the one form piece into the vector piece when you're making an isomorphism between the double and Tm plus T star m.
Mm-hmm. Right.
And I think that's how you see the generalized Vierbein popping out there.
Right. Right.
And being
Yeah.
precise about what that isomorphism actually is.
That's right. That thing works at least in the case when you have this transversality. So you have so that you have the group. If you don't have the group, then I think you need to pick some choices, like some connection or something to make it work.
I have a question, and well, I mean, you already mentioned you're thinking a little bit about E7, but I was just wondering how different the story comes out to be, because somehow, just from the experience of actually constructing these consistent truncations directly in the exceptional frameworks, in the end, somehow nothing really changes when you work with E7 and E8 once you plug in certain ansets and so on. Everything reduces to exactly the same examples, essentially, that you showed with the
Right.
spheres. So I don't know whether we've all just missed something special that we could have done, or whether once you look at it the right way, it really trivializes and looks exactly like the story you've been telling. I don't know if you've got any insight on this yet.
No, but it's also because I haven't looked at it for now some time. But yeah, no, that's a good point. Like from some perspective, it's going to E7 is not a big step. It seems very much like a natural thing to do. So it's kind of curious why it seems to break in here, and probably the reason that it breaks in here is that that we are not using the most natural definition in here. So in fact, I think we came up with a more natural definition. But we haven't yet checked whether this property of recovering the exceptional tangent bundle, whether it still holds. So yeah, so I think it probably can be traced to the fact that maybe this is not the, although this works and it's beautiful, there is maybe a more worksy and beautifully formulation that would make E7 like more in line with the other examples, and also then presumably go beyond. But interestingly, stuff breaks more and more as you go to E8 and all that, so that's kind of a nice challenge.
Okay, and maybe just another question, given that you have this slide open now, do you see any sign of something like generalized type 2b supergravity arising, just because you were looking at the fluxes and the deformations and so on, and there's some story, I guess Mark here has even done a little bit on that, with how generalized type 2b arises here, like you can...
You mean the one where you don't have a dilaton but you replace it by... Okay, that's a good question. So there is a natural way to approach that in the Courant, from the Courant perspective, where you can fit it nicely with, so that was our work with Pavel a couple of years ago. But that's the generalized geometric story. It fits in nicely, actually, surprisingly nicely. I don't know yet how to relate it to this case, but anyway, the stuff that I had here is kind of local, and locally you don't really feel much of a difference between that. But yeah, I don't. We had some discussion with Dan Waldram about this. I quite forgot, but I don't have don't have anything concrete to say. But it's a good question. It should be investigated, and it's on the list of to-do things.
Okay. Any other questions? Okay, well then let's thank Friedrich again. Okay, and well, enjoy your evenings, and I think tomorrow we start earlier, right? So make sure to check the timetable. Tomorrow is the same time, Thursday's earlier, sorry.